So hello everyone and welcome again to Professor Patrick DasGupta, and Patrick will give his second lecture on cosmology today. So welcome and you can take over.
Thank you. Thank you, Priya. All right. So yesterday, towards the end, we saw that K equal to 0 model corresponds to the FLRW flat model. That means the spatial part of the geometry is that of Euclidean geometry, while K equal to -1 model is open FLRW model. Basically, it means that the universe will continue to expand without halt till the cosmic time goes to infinity. On the other hand, K equal to +1 model, which corresponds to the test particle's energy being negative, the test particle on the surface of the sphere of co-moving radius r, that test particle's energy being negative, and therefore the ball will expand up to a maximum physical radius and then starts contracting. Such a model is a closed FLRW model. Great. But now one might ask that from observation's point of view, how do we know what kind of FLRW model describes our universe best? What do we measure? And that is where the notion of critical density becomes very important. So you can ask the question, what is the condition of the universe in order that the universe is described by the K equal to 0 model? That is, universe is the flat Einstein de Sitter model. So let's go back to our first FLRW equation. Our first FLRW equation reads A dot square by A square plus KC square by A square is equal to 8 pi G by 3 into mass density of the universe. If K is equal to 0, then our equation is simply A dot square by A square is equal to 8 pi G mass density divided by 3. But note, A dot by A is h of t, which is the Hubble parameter. So the equation therefore is h square is 8 pi G rho t divided by 3 when K is equal to 0. For the K equal to 0 model, at all times, the square of the Hubble parameter must be 8 pi G by 3 multiplied by the mass density of the universe. This is what is the condition in order that the universe is described by K equal to 0 FLRW model. Now, if we evaluate this equation at square equal to 8 pi G rho divided by 3 at the present epoch of our universe, we know h at present epoch by definition is the so-called Hubble constant at the present epoch, which is also called the Hubble constant h0. So at the present moment, this condition reads square of the Hubble constant must be equal to 8 pi G mass density of the universe divided by 3. This mass density is called the critical density because the mass density is purely given in terms of the measured Hubble constant. So in other words, from this equation, we get the condition that the universe is described by K equal to 0 model. What is the condition? The mass density of the observed universe, if it is equal to 3h0 square divided by 8 pi G today, then the universe must be described by the K equal to 0 model. And therefore, this quantity 3h0 square by 8 pi G is called the critical density at the present epoch. And this is a very important number. So, if I parameterize the Hubble constant as 100 times a parameter h0, kilometers per second per megaparsec. So if our value of the Hubble constant today h0 is 100 small h0 kilometers per second per megaparsec, then you substitute in this expression for the critical density, you find that the critical density is given by 1.88 into 10 to the power minus 29 h naught square grams per centimeter cube. Where h naught, of course, is a parameter, because yesterday's lecture I told you that there is a uncertainty as to what the value of the Hubble parameter is. H naught will be about 6.8 if you believe in the microwave background radiation precision data, while H naught will be 7.4 if you believe the JAA data for the nearby galaxies. So H naught is a parameter which is still to be ascertained accurately. But in terms of this parameter H naught, the value of the critical density is 1.88 into 10 to the power minus 29 H naught square grams per centimeter cube. In other words, all we have to do is estimate the mass density at the large scale structure of our universe and compare it to this value. And from the comparison, we can find out whether our model of the universe is given by k equal to 0 or k equal to plus 1 or k equal to minus 1. It's obvious if the density today is greater than the critical density, then obviously the universe must be k equal to plus 1. Why? Because go back to the first FLRW equation. If you look at the first FLRW equation, if the density is greater than the critical density, a dot square by a square today, of course, is the Hubble constant square. If rho is greater than the critical density, k must be larger than 0. So it is clear that when rho is greater than critical density, k is plus 1. While if rho is less than the critical density, then obviously k must be equal to minus 1. Hence, by estimating the observed mass density of the radiation plus matter at large scales meaning more than few times 100 megaparsec, we will ascertain whether universe is governed by k equal to plus 1, k equal to 0 or k equal to minus 1. Similarly, there is another parameter which cosmologists often deploy for the same purpose, and it is called the density parameter omega 0. The total density parameter omega 0 is defined to be the total mass density today divided by the critical density today. Critical density we know is 3h naught square by 8 pi g. And if the estimated mass density today of matter plus radiation on large scales is rho naught, then the dimensionless parameter, density parameter omega 0, is simply rho 0 by critical density today, which is given by this expression. And hence, this dimensionless parameter, if it is equal to 1, if omega 0 is 1, then we know our universe is described by k equal to 0 model. While if omega 0 is greater than 1, the universe is described by the closed model k equal to plus 1. While if it is less than 1, the value of k is minus 1. So, for observational cosmology, the astronomers are onto a quest for two numbers. One is the Hubble parameter today, h naught, and the other is the density parameter omega 0. So once one ascertains the value of h0 and the density parameter omega 0, one knows the exact FLRW model that describes our universe. Now we will come to the second FLRW equation. Of course, when one does general relativistic cosmology, the first and the second FLRW equation, they come directly follow from the Einstein equation. But since we are using a Newtonian description, we will use a different way of obtaining the second FLRW equation. But the surprise is, although we are using Newtonian cosmological model, the equations are exactly the same as one obtains from relativistic cosmology. We will recourse to thermodynamics to get a hang of the second FLRW equation. First, let us remind ourselves, what does first law of thermodynamics tell us? So if you have a thermodynamic system for which the internal energy is capital U, the pressure is P, and the volume of the thermodynamic system is V, and if the system's heat content is capital Q, then the first law says if you make infinitesimal changes to the system, then the change in the internal energy is equal to the change in the heat content. That is, either you put in heat or remove heat. If you put in heat, dq will be positive. If you remove heat, dq will be negative. And then from that, you have to subtract the quantity minus p dv. That means if the volume expands, then system is doing work P into dV, and therefore if the system is doing work P into dV, its internal energy will decrease. While if the volume decreases, then dV is negative. That means the outside agencies are doing work on your thermodynamic system to make it compressed, and therefore work done becomes positive because dV is negative and internal energy increases. So we know that the first law of thermodynamics tells us about conservation of energy. It says change in the internal energy is equal to change in the heat content minus pressure times dV. Pressure times dV is simply the work done, either on the system or by the system. Now what we will do is we will consider our spherical ball of co-moving radius r as our thermodynamic system. Okay, and we will apply the first law of thermodynamics to our spherical ball of co-moving radius r. Now note that our universe is homogeneous and isotropic. Therefore, the hypothetical spherical ball that we have considered, everywhere inside, the temperature must be uniform, because homogeneity implies that density, temperature, pressure, everywhere within the sphere must be independent of spatial point. Of course, there will be a time dependence, but it cannot depend from spatial point R1 to spatial point R2, because the universe is homogeneous and isotropic. And since within the sphere, the temperature everywhere is identical at a given cosmic time t, there is no temperature gradient, and therefore the spherical ball does not exchange heat with outside agencies. Because everywhere at the cosmic time t, everywhere in the universe, the temperature is identical. There is no temperature gradient, and there is no transfer of heat. And hence, dq must be equal to 0. If dq is 0, then such a system is an isolated system which evolves adiabatically according to thermodynamics. So the equation therefore will be d of internal energy is simply minus pressure times dV, because It's an isolated system which is not exchanging heat with the outside environment. Now, what is the internal energy for our spherical ball? The mass density is rho, and because of Einstein's mass energy equivalence, Einstein's special relativity says that anything that has mass m has energy mc square, or anything that has energy E has mass E by c square. And therefore, the energy density of the spherical ball is mass density rho of t into c square at time t. And therefore, the total internal energy of the spherical ball is rho t into c square, which is the energy density, times the volume of the sphere. Volume of the sphere is simply 4 pi by 3 L cube, where L is the physical radius of the ball. Physical radius of the ball is simply the cube of the co-moving radius, which of course doesn't change with time, times the scale factor cube. So A cube into R cube is L cube, where L cube is the expanding radius of the sphere. And hence, we have expressed the internal energy of the spherical ball as c square rho of t multiplied by 4 pi r cube a cube by 3. Of course, a is changing with time and rho of t is changing with time. So our first law of thermodynamics, which says d of u is equal to minus p dv, because dq is 0. And v, of course, is 4 pi r cube a cube by 3. If you put in all these values, then you get the result that d of c square rho of t 4 pi r cube a cube by 3 is equal to minus pressure times d of 4 pi r cube a cube by 3. Small r, which is the co-moving radius, is constant. 4 pi by 3 is constant. So therefore, 4 pi by 3 r cube can be cancelled on both sides, so that we have the result that d of c square rho into a cube. Remember, what I did was, because 4 pi r cube by 3 does not change with time, that comes out of the differential d, and that happens on both sides and they get cancelled, so that one gets the equation d of c square rho a cube is minus 3p a squared. Here there's a typographical error. It's not dp, but dA. Okay. So go back to this equation. Where does this equation come from? D of a cube, differential of a cube is nothing but 3a square dA. That is where 3a square come from. And note that there is a typographical error here. It is not d of p, but d of a. So we have got the result that d of c square rho a cube is equal to minus 3pa squared dA. And therefore, if I divide both sides by dA and take minus 3 by pa squared to the left-hand side, we get this equation, which reads d by dA into energy density times a cube plus 3pa square is equal to 0, where p is the pressure. All right. So either you can take this equation d by dA of c square rho a cube plus 3pa square equal to 0 as the second FLRW equation, or in general textbook, what is canonically written as the second FLRW equation is this: the second time derivative of the scale factor divided by the scale factor, that is a double dot divided by a, is equal to minus 4 pi g by 3 square multiplied by energy density, which is rho into c square, plus 3 into pressure. This in most textbooks is referred to as the second FLRW equation, but either you can take the energy evolution equation as the second FLRW equation, or a double dot by a equal to minus 4 pi g by 3 square multiplied by c square rho plus 3p as the second FLRW equation. And that's the reason I've given you a tutorial problem which says that if you use the energy evolution equation along with the first FLRW equation, you can derive the second FLRW equation. That means the three equations, first FLRW equation, energy evolution equation, and the second FLRW equation, the three equations are not independent. Only two out of them are independent. Okay. So this is a tutorial problem. Please solve and show that indeed from the first FLRW equation and the energy evolution equation, you can derive the second FLRW equation. Now note, from this second derivative of scale factor divided by scale factor form of second FLRW equation, we get a very important result. And what is this? That normally for standard matter that we encounter, whether it is gaseous matter or whether black body radiation, etc., we know that energy density is positive. We know pressure is positive, so that C square rho plus 3p is always positive. And because of the negative sign here, minus 4 pi g by 3c square, it tells me that the second derivative of the scale factor is always negative, provided C square rho plus 3p is positive. What this tells us is, if the universe has only standard matter, like normal matter made out of neutrons, protons, electrons, or made out of photons or neutrinos, so that the pressure is positive, for such a universe, as the universe expands, A dot is positive, but A double dot will be negative. That means we will always have a decelerating universe. You will say that, well, that is not very surprising. After all, gravity is always attractive. If the gravity is always attractive, then we know that because of attraction, the acceleration of matter will always be negative. There'll be only deceleration. When we throw a ball upwards, yes, the distance between the ball and Earth is increasing with time, but the acceleration is pointing downwards because the gravity is pointing downwards. So the speed of the ball keeps decreasing when it is going upwards. On the other hand, see, that is why in science, observations, experiment, and measurement, they are very important. What happened from mid 1990s is that three people, Perlmutter, Schmidt, and Brian Schmidt, Perlmutter, and Rees, R-E-I-S-S, Rees, they monitored the type 1a supernovae, their apparent magnitude versus redshift. And from that, of course, for type 1a supernovae, one can show that the absolute magnitude acts like a standard candle. And from that, they showed that in late times, that is for redshift less than 2, our universe is displaying acceleration in the expansion. That means what? The second time derivative of the scale factor is greater than 0. Now that is very surprising, because we would expect that gravity, being attractive, should always have the deceleration, After all, this second FLRW equation itself is showing that for normal matter, since pressure is positive, energy density is positive, A double dot is negative. But observations, if you indeed believe that the type 1a supernovae may be taken as standard candle, then the universe shows accelerated expansion in late times. How can that be? Well, from here itself, from the second FLRW equation itself, we can explain that by saying that there is a strange kind of matter for which the pressure is so negative that energy density C square rho, so C square plus 3p is negative. If C square plus 3p is negative, then a double dot, that means second time derivative of the scale factor, can be positive. And currently, what you hear about dark energy is nothing but a kind of exotic matter which is today dominant. And for this exotic matter, c square rho plus 3p is negative. And such a dark energy can explain why the universe is showing late time acceleration in the rate of expansion of the universe. Right. Now, we have already seen the energy evolution equation. The energy evolution equation is this, which says d by dA of energy density times the physical volume a cube plus 3p a square is equal to 0. This energy evolution equation is very important. This tells us how different kind of matter, how the energy density falls off as the universe expands. We will show it for 3 cases. Okay, we will apply this energy evolution equation for 3 different cases and will illustrate how this equation plays such a very important role. First, we will apply it to dust-like matter. Normally, when we look at dust, we see that when someone sweeps a dusty road, you see suddenly the air is filled with dust. But these dust particles, they don't have much random motion. Soon afterwards, they fall onto the ground because of the gravity. If it was having sufficient pressure, there will be a hydrostatic equilibrium and they will not fall onto the ground. But because the dust particles, they don't have appreciable pressure, soon afterwards they settle down on the ground. So matter for which pressure is negligible compared to its total energy density, they are termed as dust-like matter. So when the universe is in a state where the dominant content of the universe consists of entities with random speeds much less than the speed of light c, such entities behave like dust-like matter and their pressure can be approximately set to 0. If you set the pressure to be 0, then from our energy evolution equation, if pressure is 0, we get the equation d by dA of c square into mass density times a cube is equal to 0. That means c square rho a cube is a constant. In other words, we get the important result that for dust-like matter, the mass density as the universe expands falls as 1 over cube of the scale factor. So in other words, for dust-like matter, mass density is equal to some constant k divided by the cube of the scale factor. Of course, you can intuitively understand why this must be so. For dust-like matter, the mass density is simply the sum of the mass of the particles divided by the volume, and the volume increases as a cube, and therefore the rho of t has to go as k by a cube of t. That's a very simple intuitive explanation why we must have such a result. Now, what we can do is that if our universe is dominated by such dust-like matter, then we can immediately use this result in the first FLRW equation and obtain the scale factor as the function of time for k equal to 0 model. Why? For k equal to 0 model, our first FLRW equation will say a dot square by a square, because k is 0, a dot square by a square will be simply 8 pi g by 3 into rho of t. But rho of t for dust-like matter is k divided by a cube. So I get 8 pi g k by 3 a cube in the right-hand side. In other words, a square in the denominator on the left-hand side and a cube on the denominator at the right-hand side there'll be a cancellation so that I get the equation a dot square is 8 pi gk by 3a, which means if I take the square root, I'll get a dot equal to k1 by square root of a. Note, I have taken the positive square root. A dot square was this. If I take the square root, I get plus minus. But because we are talking about an expanding universe, for expanding universe, a dot is positive. So I've taken the positive square root. Had the universe been contracting, that means Hubble would have seen blue shift in the emission line wavelength instead of red shift, then our universe would have been contracting and I would have taken negative square root. But our universe from observations happens to be positive because emission lines are shifted towards the red end and therefore universe expanding and a dot therefore is positive. I take the positive square root and a dot therefore becomes k1 by square root of a. Then I can take square root of a to the left hand side so that I get square root of a dA is equal to k1 into dt, because dA by a dot is dA by dt. dt part I'll take to the right hand side. And this equation can be easily integrated. If you integrate both sides, I get the result that a to the power 3 by 3 by 2 is k1 into t. And hence, by integration, we get the result that a to the power 3 by 2 is 3 by 2 k1t. In other words, a of t is proportional to the cosmic time to the power 2/3. So what we have proved is that for k equal to 0 matter dominated universe, the scale factor increases as cosmic time to the power 2/3. Okay. And this is matter dominated. Why? Because we are talking about the matter having speed much random speed much less than speed of light, so that non-relativistic matter is essentially in the form of non-relativistic matter. Radiation part is negligible. So therefore, for matter dominated universe, when k is equal to 0, we have exact derivation of the scale factor going as the cosmic time raised to power 2/3. Here is another tutorial problem, because we know that Hubble parameter is a dot by a. Since a of t is t raised to power 2/3, you can immediately find out what is a dot. So tutorial problem 2 asks you to show that when scale factor goes as t raised to power 2/3, then show that today the age of the universe t naught is equal to 2 divided by 3 times the Hubble constant today. This is a very important result, because from this result you can show by measuring the Hubble constant, you can infer what is the age of the universe today. So please do this tutorial problem. It's a very trivial problem, but nevertheless, do this problem so that you get a hang of how you can apply the concepts we are learning. Next, we will apply the energy evolution equation to radiation like matter. Okay. So suppose the content of the universe is dominated by ultra-relativistic matter like photons and particles which are having high momentum compared to their rest mass. So those are ultra-relativistic matter, because from special relativity we know that there is a equation relating energy and momentum. Energy is given by square root of p square c square plus m0 square multiplied by c4, where m0 is the rest mass. If the momentum is much high compared to the rest mass, then energy is approximately p into c, where p is the momentum. For such ultra-relativistic matter, one can show that the pressure at any time is energy density at that time divided by 3. You can intuitively see why this factor of 3 comes up, because for ultra-relativistic matter, just now I argued, momentum is equal to energy divided by c approximately. So therefore, if they are randomly moving in different directions, all right, so average momentum, they are not orderly moving in particular direction. So average momentum will be 1/3, and therefore it will be 1/3 the energy density. So for ultra-relativistic matter or our electromagnetic radiation, photons. For photons, pressure for a thermodynamic system of photons, pressure is always 1/3 energy density. And if you take ultrarelativistic matter, then approximately pressure is energy density divided by 3. So if we substitute for the pressure c squared rho divided by 3 in the energy evolution equation, so that we get d by dA into energy density times AQ is 3 into pressure, which is c square rho by 3. So this 3 will cancel. I'll get the equation d by dA of rho AQ plus rho A square equal to 0. Then what we do is we multiply both sides by the scale factor A, so that I get the equation A multiplied by d by dF rho AQ plus rho into AQ, because I have multiplied A on both sides. And this is nothing but simply d by dA of c square rho into A4. So in other words, what we have derived is that for radiation-like matter, from the energy evolution equation, we get the result that d by dA of c square rho multiplied by A4 is equal to 0. What this tells us is that the energy density for radiation-like matter falls off as some constant K2 divided by scale factor to the power 4, because rho into scale factor to the power 4 is a constant. D by dA of rho into A raised to the power 4 is 0. Can we understand it in a simple physical intuitive manner why we expect for radiation-like matter energy density must fall off as 1 over A4? The answer is very easy. The number density of ultrarelativistic particles, that should of course fall as 1 over A cube, because the total number of particles in a co-moving sphere, that total number is constant. So as the sphere increases its volume as A cube, the number density should fall off as 1 over A cube. But energy density is nothing but h nu, where nu is the frequency of photons, h nu into number density. But nu, because universe is expanding, wavelength is getting stretched out. So at T1, if the wavelength is lambda 1, then we know that lambda 2 at T2 will be more than lambda 1, and lambda 2 will be simply lambda 1 into A T2 divided by A of T1. So the redshift that the lambda, because of stretching, the redshift that happens is simply the scale factor now divided by the scale factor at which the photon was emitted. So the frequency falls off as 1 over A, because the redshift stretches out a wavelength. Wavelength stretches out as A of t. Frequency being speed of light divided by wavelength. Frequency falls off as 1 over A. So energy of the photon falls off as 1 over A. Number density falls off as 1 over A cube. So the energy density falls off as 1 over A to the power 4. That is a simplified manner why we can explain intuitively why the energy density of radiation-like matter goes off as 1 over A4. Okay. Now that tells us one very important fact. We found that the energy density for non-relativistic matter falls off as 1 over A cube, but the energy density of relativistic, ultra-relativistic matter falls off as 1 over A4. Just now we derived it. What this implies is that if we start off at some time in the universe with equal amount of non-relativistic matter and ultra-relativistic matter, then the energy density of ultra-relativistic matter will fall off faster because it's going down as 1 over A4, while energy density for non-relativistic matter is going down as 1 over A cube. So it is falling off slower. So what this tells us is, as universe keeps expanding, after a while, it is the non-relativistic matter which will start dominating, because energy density of relativistic matter is falling off faster. And that is what happens in the universe. When the universe began in the early time, the universe was dominated by ultra-relativistic matter-like object, but as the universe expanded, it is a non-relativistic matter which took over. So today, the universe is largely dominated by non-relativistic matter like Earth, planets, sun, stars, galaxies, etc. All right. While the radiation content, which is given by the cosmic microwave background radiation, is cooled down to 2.7 degree Kelvin. Its energy density is far less today compared to the non-relativistic matter. It is because of this feature that ultra-relativistic matter, its energy density goes down as 1 over A4, while non-relativistic matters, its energy density goes as 1 over A cube. Now, what we do is we can use this form that rho is going down as 1 over A4 for radiation-like matter. We can use the first FLRW equation and take k equal to 0 model to find out how scale factor changes with time when the universe was radiation dominated. For k equal to 0, therefore, the first FLRW equation will say a dot square by a square is 8 pi g by 3 square into the energy density, which is going as 1 over a4. So a dot square is proportional to 1 over a square, which means taking the square root, we get a dot proportional to 1 over a, which is simply a dA by dt is equal to a constant k3, and therefore a dA is k3 dt. It can be easily integrated, and when we integrate, we get a square is 2k3t. In other words, the scale factor goes as square root of the cosmic time of the universe. So in the radiation dominated part of the evolution of the universe, scale factor grows as square root of the age of the universe. While later in the matter dominated universe, for k equal to 0, the scale factor grows as cosmic time to the power 2/3. Now from here we can conclude a very important result. And what is that? That if our early universe, which was very hot, as I said, in the past, universe was dominated by radiation-like matter. And in the past, if the content of the matter was in the form of black body radiation, for black body radiation, we know from the Stefan Boltzmann law, the energy density is the radiation constant AB times 4th power of the temperature. From our school days, we have learned the Stefan Boltzmann law for black body radiation. So early universe, which was dominated by hot radiation-like matter, the energy density goes as the radiation constant AB times 4th power of the temperature of the radiation. But we have already proved that for radiation-like matter, the energy density also goes as 1 over A4. Comparing these two equations, that energy density is proportional to 4th power of the temperature, while the energy density is also proportional to 1 over 4th power of the scale factor, we find that the temperature of the radiation falls as 1 over A of t as the universe expands. So we have got a very important result that when the early universe was very hot and the universe is expanding, the temperature as the universe expands, the temperature falls off as 1 over scale factor. And that is precisely the reason today the temperature of the universe, when I say temperature of the universe, what do I mean? Temperature of what? Is the temperature of the photons, background photons, which is currently in the form of cosmic microwave background photons. Today, the temperature of the cosmic microwave background photons is 2.73 degree Kelvin. Very low, while when the universe was 380,000 years old, today the universe is about 13.8 billion years old. When the universe was 380,000 years old, the temperature of the universe, temperature of the photons was high. It was about 1100 degree Kelvin. I will later on, if I have time, I'll tell why this 1100 degree Kelvin is important. But let us go ahead with the cosmology so far. So what we have deduced, therefore, is that early universe was very hot. As you go back in the past, A of t becomes very small. And in fact, the Big Bang epoch was when A of t is 0. A of t 0 is the Big Bang epoch. That means the scale factor 0 is the time when the Big Bang actually happened. That time the temperature was infinite. Okay? From classical general relativity. Of course, people believe that when you take quantum gravity into account, A of t cannot be 0. It will be of the form of Planck's scale. Right. The third tutorial problem is that from this relation that temperature is going as 1 over A of t, and we have already proved that for radiation like matter, A of t goes as square root of t. Prove this result that that is called time temperature relation. The time temperature relation reads as temperature of the universe is 10 to the power 10 degree Kelvin multiplied by the cosmic time of the universe in units of 1 second. That means t, the cosmic time divided by 1 second to the power minus half times 10 to the power 10 degree Kelvin is the temperature of the universe at any given time when the universe was radiation dominated. There's a very important result. This tells us as you go further and further back in time, the temperature of the universe increases like hell. In fact, that is the reason why high energy physicists are interested in the early universe, because when the temperature is very hot, the random velocities of the particles are very high, and therefore particle physicists can test their particle physics model by going back into the theoretical early universe consideration, because in the past the random particle velocities were very high, and they can use new theoretical particle physics model to see what implications they have on the conditions of the early universe. And that's the reason why this time temperature relation is very important. I will finally talk about one application of the energy evolution equation, namely the vacuum energy. If you study quantum field theory, you will see that the vacuum meaning the no particle state in quantum field theory, the vacuum's energy is not zero. Just like when you do quantum mechanics of harmonic oscillator, you know the ground state energy of the quantum harmonic oscillator is not zero. It is half h bar omega, where omega is the natural frequency of the oscillation. Similarly, one can prove in quantum field theory that for every vacuum mode, there is a half h bar omega k vacuum mode of energy, so that the vacuum is seething with energy. And for the quantum field theoretic vacuum, you can show the pressure of the vacuum is negative of the energy density of the vacuum. If you study quantum field theory, one can show that the vacuum, which is non-trivial in quantum field theory, the pressure of the vacuum is minus of energy density. If you use this in our energy evolution equation, what will you get? You will get d by dA of the vacuum energy density c square v vacuum into a cube plus 3pa square, but pressure is minus c square rho vacuum. So therefore, you will get minus 3c square rho vacuum a square, which implies the equation, if you differentiate, take d by dA of c square v vac first, a cube as it is, and then c square v vac dA cube by dA, then you will get the result. When you differentiate this, you'll get c square a cube d vac by dA plus 3c square vac a square. Where does this come from? D by dA of a cube is 3a square. So you get 3a square. But this term cancels with the negative term, and you get the result that d by dA of mass density of the vacuum is 0. In other words, from our first FLR, sorry, it is from our second FLRW equation, we get the result that the quantum field theoretic vacuum is such that the energy density of the vacuum remains always a constant, whether the universe expands or universe contracts. This is exactly like the cosmological constant. Einstein had introduced cosmological constant to do something else, to obtain a static universe, but cosmological constant acts as a universal repulsive agency. And what this exercise we have just now done shows that the vacuum energy density is always a constant. It cannot be distinguished from cosmological constant. In fact, there's a whole new puzzle called cosmological constant puzzle, which emerges from this. I would not like to talk about this. Anyone interested can read an article that I had published in Resonance. You can get it also in archive just by, in the Google search, if you type the mystery of the cosmological constant. So this brings us to the last tutorial problem. Please show, by using the fact we have just now derived, that rho vac is always a constant. If the universe is dominated by vacuum energy, then show that for k equal to 0, using the first FLRW equation, show that scale factor can be exactly derived to be going proportional to e raised to power k0t. That means if the universe is vacuum energy dominated, the universe expands exponentially. This also has an implication in early universe, so-called inflationary paradigm of the early universe. Again, I will not go into it because that is another separate topic of cosmology. But the basic factor is that if the universe has any form of matter for which energy density remains constant, for such a universe, scale factor exponentially grows. As you can see, for this model, the A double dot will obviously be positive. Why A double dot will be positive? Because A of t itself is exponentially growing, but that's not surprising because for the vacuum energy, pressure is negative, so that 3 times pressure times c square rho vacuum is negative. So obviously we'll get an accelerating model. And in fact, that is how people explain the present accelerating phase of the universe due to a cosmological non-zero value of the cosmological constant. Right. In the remaining time, by the way, the other part of the tutorial problem asks you to get K0, the constant K0, in terms of rho vac. I have very less amount of time. What I will do is that I will now just qualitatively describe the evolution of the universe. So I'll stop sharing this file. I'll go back to my other thing where I can quickly summarize the evolution of the universe. Okay. All right. So I will just talk about the evolution of the universe. Are you able to see the screen?
Yeah, yes.
Very good. Yeah, I'll just go to the full screen mode. Okay, so we have seen this figure. So what we have considered is that we talked from the point of Newtonian cosmology, we derived the right equations that describe the evolution of a FLRW universe. We saw for the closed model it'll expand, reach a maximum size, again recollapse. While for the k equal to 0 and k equal to -1 model, it'll keep on expanding. But today, from the type 1 supernovae, we know that the universe today is accelerating. So scale factor after some time will be increasing exponentially, all right? And we saw that even though universe starts out in the early universe as hot radiation, but because of the universe expanding, the temperature drops down. And this was indeed accidentally discovered by Penzias and Wilson, two microwave engineers who had built very accurate horn antenna for microwave, and they accidentally stumbled on discovering the cosmic microwave background radiation. And today we know by various satellite probes of cosmic microwave background radiation, from Kobe to WMAP to Planck. I don't know whether Tarun Sauradip has talked about this, because he has been working with all these missions in a very, very active manner. So today we know that the temperature of the microwave background radiation has been accurately determined, and it is having a black body spectrum with a temperature of 2.725 degree Kelvin. And it is this which conclusively it corroborated the prediction of the hot Big Bang model. So what we have seen is that the universe began around 13.8 billion years ago, when the scale factor was close to 0. And during that time, the universe on an average was homogeneous, but there were quantum fluctuations all about. And these fluctuations grew to give rise to the galaxies that we observe today. And so this is from the time temperature relation that I showed, we know early enough for Planck time scale, classical general relativity cannot be trusted. So you have to rely on some quantum gravity model, whether it is superstrings or Ashtaker's inspired quantum loop loop space quantum gravity or whatever. And then as the universe expands, it cools down at different time. The temperatures are different, and therefore different physics becomes important. When the temperature was 100 GeV equivalent, that is when the time was 10 to the -10 seconds, the electroweak phase transition took place. While, as I told you, about 380,000 years, when the age of the universe was about 3 × 10⁵ years, the temperature of the universe had fallen down to about 1100 degree Kelvin. And at such temperature, the photons did not have energy to split an electron proton combining to form hydrogen. And therefore, when the universe cooled below 1100 degree Kelvin, when the universe was only about 380,000 years old, then electrons and protons predominantly combined to form hydrogen atom, and the universe became neutral. And these photons, therefore, no longer interacted effectively with matter, and they froze out. And today, when it has cooled down to 2.725 degree Kelvin, we are seeing those photons as microwave photons. And since the neutral matter had formed, they slowly formed, in the presence of dark matter, they formed big structures like clusters of galaxies, superclusters, and galaxies. All right. And I don't have time to talk about dark matter. If there are questions, I'll talk about dark matter, how we inferred that we have dark matter. This goes back to clusters of galaxy and Zwicky, analyzing clusters of galaxies and showing that the random velocities of the galaxies in the clusters are so high that unless you have unseen matter to keep it bound, these galaxies would have escaped long time back. And that was the first hint in 1933 that dark matter is present. Then later on, Vera Rubin, she mapped out the outskirts of galaxies using 21 centimeter lines of hydrogen, and showed that the rotation velocities of far-flung neutral hydrogen clouds, instead of going down, they remain flat when you go to distances more than 50,000 light years from the center of the galaxy. While if the matter as shown from the photometry of the galaxies, after this region, you don't see any matter. So if you say that only luminous matter is what is there to galaxies, then after you move out to scales above 50,000 light years, since there is no matter, the rotation velocity v square by r being equal to gm by r, that is the centripetal force equal to gravitational acceleration, your rotational velocity should have decreased, but it doesn't decrease. Rather, sometimes, in fact, it increases beyond the realm of the visible part of the galaxies. That shows that there is some kind of dark matter halo around our visible matter. So the dark matter halo extends up to 1000 kiloparsec, while the radius of a typical galaxy extends up to 30 kiloparsec. And therefore, the dark matter content, which is also seen from the clusters of galaxy, is a cluster of the galaxy. And you can see the arcs, these are the Einstein rings due to the gravitational lensing of a background object due to this cluster. From the Einstein ring also, you can estimate the total matter. And the total matter, indeed, the mass is much more than the mass which you can estimate from the luminous part of these galaxies, showing that there is dark matter. And so indeed, the gravitational lensing. So this is a cluster of galaxies. So there is a dark matter halo from the Einstein ring. We can indeed infer dark matter halo. And then the bullet cluster, where two clusters colliding, showed the luminous matter after the cluster crossed each other. Luminous matter were clumped here, while the dark matter part were clumped here, because dark matter do not interact with each other. They simply pass through each other, while the luminous matter, they interact electromagnetically, they get slowed down. So there is great observational evidence that there is dark matter, and from type 1a supernovae, there is evidence that there is dark energy. So the universe, in fact, is dominated by dark systems. 73%, about 70 to 73% is in the form of dark energy, 23 to 25% in dark matter, while the standard matter that we are made up of, atoms, etc., they are only 4 to 5%. So most of the matter of the universe is dark. Dark meaning they don't interact with electromagnetic waves. Okay, we can only infer them from their gravitational impact. So in other words, dark things like dark chocolates and dark matter and dark energy, they are indeed attractive, and current cosmology research is going in an accelerated pace on these things. I will not discuss the other results. So things like how supermassive black holes were formed, whether the dark matter are in the form of primordial black holes, or what I'm working on, if the dark matter is in the form of ultralight dark bosons like axions. So we still don't know what is the form of dark matter. So I will stop here, and it is more important that I take questions.
Questions?
Thanks so much, Patrick, for a lovely talk. Just that
Most
we could share
welcome,
some
Priya.
chocolates. We could have shared some chocolates if this was an
Yes.
offline thingy.
There's a question from Ankur.
Yeah.
Yes.
He writes, "Thank you, Professor. This is such an interesting talk. Does non-zero vacuum energy imply that they are virtual particles popping into existence and annihilating all the time?"
Most welcome, Ankur. Yes, you're right. The vacuum energy indeed can be also viewed as spontaneous creation of virtual pairs of particles. And we know such a thing indeed is there from the experimental measurement, so-called lamp shift. As you know, the energy levels in the hydrogen atom, they are not exactly given by the levels as predicted from Dirac theory of electrons around hydrogen atom. There are tiny shifts, and this shift is due to the vacuum energy and can be understood as virtual creation of electron and positron between the atomic nucleus and the electron cloud. And because electron and positron pairs are being virtually created, they act as a dielectric and screen the attractive force due to the nuclear positive charge on electrons and cause shift in the energy level. And these shifts have been measured accurately, and they indeed agree with the dynamic vacuum that is predicted from quantum field theory. Yes, that is true, but the biggest problem, which is the so-called cosmological constant problem, is that if you calculate the vacuum energy as predicted from quantum field theory, the vacuum energy density goes as the fourth power of the inverse of the Planck length. Okay. Planck length, as you know, is of the order of 10 to the minus 33 centimeter. It is a tiny thing, which is the Planck length is a combination of Planck's constant, Newton's gravity, and speed of light. And so quantum field theory predicts the vacuum energy density to be extremely high. On the other hand, the accelerated expansion of the universe tells us that the acceleration is not very high. From that, the net energy density should be 10 to the minus 120 times what is predicted by the quantum field theory vacuum energy density. And therefore, one would like to explain this by saying, well, there is a cosmological constant which arises in classical general relativity as posited by Albert Einstein in 1916 or 17. While the vacuum energy density, since it also acts like a cosmological constant, you can cancel both of them, but the cancellation must be to such a accurate order that the net result is 10 to the minus 120 times what is predicted from quantum field theory for the vacuum energy density. That means the bare cosmological constant and the bare vacuum energy density must cancel to this such a tiny precise level, and this is called the fine-tuning problem in cosmological constant. And people had been trying to solve how to do this fine-tuning, and there is no so far good answer, and this is called the cosmological constant problem. And that's the reason why many people believe that the accelerating universe should not be explained in terms of cosmological constant, must be explained by an evolving dark energy. But the jury is still out. We still don't know what exactly is causing the accelerating universe. But what is very surprising is the measurement, astronomical measurement tells us that whatever is the dark energy, it is very much like the vacuum energy. That means the pressure of this so-called dark energy is minus 0.9999 times the energy density. It is as though it is minus energy density itself. That means the parameter, the pressure divided by the energy density, is close to minus 1. Minus 1 will be for vacuum energy density, while it should be any other value for dark energy. But observation tells us that it is close to 0.99. So indeed, we are in a very exciting phase, and soon there'll be new discoveries which will throw complete surprise. As it is, there is a tension between the estimate of the Hubble parameter. So we are living in exciting time as far as cosmology is concerned.
Here's another
Yeah,
question.
thank you, sir. I have another question. May I go forward with it?
Oh yeah, of course. The whole idea in science is you must not believe what the speaker has said. You must try to prove me wrong. That's what I tell my students.
Right. So, sir,
Prove me wrong.
it is. Yeah,
Yeah,
it is related to dark matter. What is your take on the Mond theory, and does it relate or have any correlation with the Newtonian cosmology?
right, good. So Mond theory, as Milgrom, those who are in the know of Mond theory, Milgrom, he postulated a very exciting idea. He said that, well, where the rotation curve is getting flattened out, there the acceleration is very tiny. So he decided, well, how do we know that Newton's laws are valid for all acceleration? He posited that when the acceleration is below a particular value, probably Newtonian dynamics have to be sort of modified. And therefore, he gave a modified Newtonian dynamics called MOND and tried to explain the rotation curves. Rotation curves, Milgrom could explain very nicely. But the problem comes when you try to use the simple model for all kinds of different evidence for dark matter. For clusters of galaxies, you see rotation curve, because spiral galaxies have a definite rotation, while for clusters, galaxies are moving randomly. So for clusters of galaxies, if you try to use MOND, you have to fine tune your parameters. There are 2 or 3 free parameters. While if you try to use for bullet clusters, your parameters then change. So therefore, a theory which should be, the parameter values should be changed from case to case, doesn't appear to be a fundamental theory. Okay, a fundamental theory, there should not be more than one parameter. While MOND-like explanation for as alternate explanation for dark matter problem, it is sort of besieged with more than one free parameters that you have to tune by looking at the observations. And furthermore, there is no general extension of MOND-like theory to relativistic regime. We know, for example, Newtonian gravity and Newtonian dynamics come as an approximation of special relativity and general relativity. In fact, if you know special relativity and general relativity completely, then you can derive Newton's laws of motion, Newton's gravitational dynamics as approximation. While MOND, there is no direct relativistic analog, although Milgrom and others have tried to give a relativistic model, but if you look at them, it is extremely untidy. While general relativity, the mathematical beauty of general relativity is enormous. And normally and remember, in general relativity, there are no free parameters at all. The only parameters in general relativity that appear are gravitational constant capital G and speed of light c, but they were there all the time. They were not new parameters. So general relativity is one theory which predicted new effects that were corroborated by experiment, and it did not posit or it did not put forward any new parameters. And that's the reason why people favor general relativity, and within general relativity, as I have just showed in these lectures, that you can explain repulsive gravity also. All you have to postulate is some kind of a matter for which pressure is negative. If energy density plus 3 times pressure is negative, from general relativity itself, we can have repulsive gravity. So in other words, a model with minimal set of assumption is that of having dark energy and dark energy matter without modifying either Newtonian mechanics or Newtonian gravitational theory. That is my personal opinion, and that happens to be also the opinion of majority of cosmologists. But yes, well, who knows, further experiments might overturn whatever I have said so far. And that is what is exciting about fundamental physics and fundamental astrophysics, that you are always in for a surprise. And that is what keeps us going, right? That is what keeps us always excited.
There's one more question.
Yes.
Two more.
Two more on that.
Yeah, as much more the merrier.
Yeah. Yeah, one second.
Energy.
Yeah. So one was, I think this right. As the vacuum energy density is constant as the universe expands, how does energy conservation take place?
Oh, that's a very good question. So that's a very good question. Go back to my, okay, so let me go back to my tech file. So I'll stop this sharing this, and then I'll share the tech file again. That's a very good question. Yeah, so are you able to see the tech file again?
I can see it.
The tech file which I had shared earlier. Can you see page number 13, tutorial problem 4?
Yes, yes.
Yeah. Okay. So let's go back to our thermodynamic equation. Yes. So the first law of thermodynamics, are you able to see page number 7? Where the first law of thermodynamics has been stated, du equal to dq minus pdv.
Yes, we can see that.
Very good, very good. Okay. Now, if your pressure is negative, see for the vacuum energy, pressure is negative. If pressure is negative, forget the dq. As we said that for an isolated system, dq is 0 so that it expands adiabatically. So when pressure is negative, du is a positive quantity times dv. Okay. So when the volume increases, actually the system does not, the increase in the energy d of u is the energy density times volume. So d of energy density times volume, and pressure is negative and it is energy density itself. So you have d of energy density into volume is energy density into d of v. So in other words, this tells me d of energy density times volume is equal to energy density times d of volume itself says energy density is constant. In other words, the reason why the energy density is a constant is when the pressure being negative, when the volume is increasing, there is negative work done by the system because the pressure is negative. And negative being work done, meaning the energy remains constant. So even from the first law of thermodynamics, if you have a exotic thermodynamic system for which pressure is negative of internal energy density, then you will have d of internal energy density times volume is internal energy times d of volume, which means internal energy remains a constant. Okay. In other words, what it tells you is that as the volume increases, instead of the system doing work and losing out energy, the system does negative work so that it doesn't lose energy. So have I answered the question?
Yes. I've got that. But does it mean that there is somewhere some energy increase or some input of energy or something like that? If we assume that the total energy of the universe is 0?
Not really. You can't estimate the total energy of the universe because the universe is infinite in extent. You can instead say you take a small volume like our sphere of co-moving radius r, and you can ask for a sphere which is expanding how its energy is changing. For the total universe, you can't. For the sphere, with the total energy, universe has an infinite volume. So total energy will, if it is negative, it will be minus infinity. If it's positive, it will be positive infinity.
Yes.
You can't work out. But for a sphere of co-moving radius r, if the sphere is populated by vacuum energy, then d of vacuum energy density times volume is equal to, because minus p is minus of energy density of vacuum, which is positive energy density times d of v, which means energy density of vacuum remains constant. From the work done point of view, normally for positive pressure, d of EU equal to minus p dv means when it expands, because the system is doing work to expand, therefore the work is coming out at the expense of its internal energy. But when the pressure is negative, there is the system, when it is expanding, is actually doing negative work, and therefore the total energy increases instead of decreasing. Where the volume is increasing, the total energy is increasing, meaning the energy density is a constant. Okay.
Yes, thank you.
But since you have asked a question, there is a related part. When Hoyle and independently Bondi and Thomas Gold, they gave their steady state model where the universe looks the same all the time, the density of the universe remains same, doesn't fall down. How did they explain? They explained by saying the density remains the same. They were not talking about vacuum density. They were talking about normal density of stars and galaxies. And in the steady state model, the universe has to look the same. For normal stars and galaxies, when they said that they remain constant, all the universe expanding, they had to theorize that there must be spontaneous creation of matter to maintain the density. But remember, they were not talking about vacuum energy. And then Hoyle and Narlikar being Jayant Narlikar, Hoyle and Narlikar, they proposed a C field cosmology where the C field represent creation field. The C field created the extra particles to maintain the steady state. But they were not talking about vacuum energy. It was about actual particles being created so that the actual density of stars and galaxies remain constant.
Okay, thank you very much.
Most welcome.
There's one more question from Ayush. He asks, have any inferences been made about dark matter or dark energy from Cmbr itself?
Oh yes, of course. The cosmic microwave background radiation, since the observation is very accurate, they do the best chi-square fit. And if you look at their data, they favor, to more than 95% confidence level. You're also doing a statistics course alongside, so you'll understand what I'm saying, that at confidence level more than 95%, the CMB data, in particular the Planck data, has come out with the best fit parameters. In the best fit parameter, they find that cold dark matter particles. What are cold dark matter particles? The dark matter particles which when they went out of the thermodynamic equilibrium, they were non-relativistic and therefore cold. So such dark matter particles are favored with energy density close to 25% and with a 5% energy density in normal matter like protons, neutrons, and electrons, and 68% or so in dark energy. And of course, as I said, the Hubble constant as the best fit parameter comes out to be close to 68 kilometers per second per megaparsec. These are their best fit parameters. But of course, CMB, the theory of CMB has some assumption like baryonic acoustic modes due to silk damping and so on. There's a lot of theory also which goes in. And therefore, the last word regarding the deductions from cosmic microwave background radiation precision study is still to be made. And that is the whole excitement, that who knows that things will change with newer set of observations.
Here's one more from Gauri Shankar. Thank you, sir, for your wonderful talk.
Most welcome.
Is it possible to have clumps of dark matter along showing gravitational lensing?
Yes, in fact, if you take an individual galaxy, then the individual galaxy is embedded in a dark matter halo. But if you go to cluster of galaxy, a rich cluster of galaxy, there are 1,000 galaxies, each with their dark matter halo. And of course, there's a diffuse dark matter halo for the entire cluster itself. Yes, dark matter can form clumps, and it would be interesting whether you'd have pure dark matter clumps without having any baryonic matter in them. So such dark matter clumps, you will never see them using your telescopes, because telescopes record electromagnetic waves in the form of either visible photons or X-ray photons or UV photons or infrared photons or gamma ray photons, etc. So if your dark matter clump doesn't have any baryonic matter, they will go undetected from your astronomical observation. But then lensing, if behind this dark matter clump, if there's a quasar, then a single quasar can either be visible as more than one image due to lensing, or if the quasar is placed in the straight line joining U, dark matter clump, and the quasar, all three are collinear, then you will see Einstein ring and all that. But the dark matter clump has to be very massive. Otherwise, the separation of the lens images will not be large enough for telescopes to detect the gravitational lensing. And people are trying to see such signatures.
Okay, thanks a lot, Patrick.
Most welcome.
Lovely session. Both the lectures were excellent, and
Thanks.
we learned a lot. And we are confident that you won't mind if these people come back to you with doubts or queries.
Yes, absolutely.
Yes.
I will send you the latest PDF. Yesterday, what I sent was not complete, because what I had sent was pertaining to yesterday's lecture. And since I have covered today much more, I will send an updated version of the PDF, which can be circulated to all the participants, and they can also do the tutorial problems.
Thanks a lot. And we'll put a link to your article in Resonance too.
Oh, yes. And also those who are interested in a very introductory sort of exposure to general relativity, there's also another preprint called General Relativity for Pedestrians. I will give the links to both of them so that those who want to go beyond Newtonian cosmology and study general relativity can also peruse those articles.
Yeah, that will be great.
I will send you the links.
Yeah. We'll put the links on our resource